Okay, now let's begin with the new topic now, our last topic before starting the actual core material of calculus, which is differentiation. So these are main keys, main machines behind differentiation. Now the next thing is continuity. So that's our new topic. Roughly speaking, a function is continuous if you can draw its graph without taking your hand off the board. Okay? But of course, that's even though it's a satisfactory definition for most of us. So we know that if you go to atomic scale, the pen never touches the board anyway. Actually, your hand is not touching the pen. Okay, so this definition is not very precise. Okay? So that's the reason we have to give a technical definition for continuity so that everybody has the same thing. Again, using the definition would be complicated, but then we'll find a way of using this definition to our advantage in practical life. Okay, so continuous functions. So a function f is called continuous at x equals x sub 0 if, so the definition is this, both of this, the word continuous and the point enters. So this is saying what happens at a particular point. If limit of f of x as x goes to x sub 0 is equal to f of x sub 0. Okay? So we take this one. So this actually means three things. Okay, so one, it means limit as f of x as x goes to x sub 0 exists. And two, it says f of x sub 0 exists. So for example, if this was sine 1 over x, we know that sine 1 over x evaluated at x equals 0 does not exist. It doesn't give you a number. Okay? And three, these two values are the same. Okay, so we summarize these three and write it like this. So in some books, they define continuity at x sub 0 if the following three conditions hold, and they write these things, three things, one by one. We summarize it in one equation like this, with the understanding that the equation is not claiming to make sense if either one side does not exist. All those numbers exist and they are the same. Okay, then we say our condition holds. Then we say the function is continuous at this particular point. Okay, and of course, generally we are interested in functions. We are interested in good functions. A good continuous function is continuous at every point on its domain. It must be continuous everywhere. Okay, so we also say that. So we say f is continuous on an interval, say I, if f is continuous at x for all x in I. So it is continuous at every point. So I emphasize this because continuity is something that you check at a singular point, at one single point. Okay? And a function continuous on an interval means that I checked it at every point. Of course, in practical life, you don't check those infinitely many points. There are ways to recognize a function is continuous. Okay? And sometimes you say f is continuous without mentioning the interval. It means that wherever f is defined, it is continuous. Okay? So that's so much for the terminology. Then question is, Why do we need this definition? Okay. So answer is the following. If I know for some reason somebody told me whatever, okay, we'll come to that. If I know that f is continuous, I can calculate its limit very easily. Okay, so now this is theoretically nonsense, because how do I know that f is continuous? Because I calculated its limit everywhere. And where will I use it? I will use it to calculate limits, but I already calculated limits. Okay, so fortunately it doesn't work like that. We'll find a way of recognizing continuous functions very easily. Okay, so another way of writing this equation is the trivial expression that you take the limit inside. That's trivial in simple problems, but sometimes in complicated examples, you will appreciate that this alternate definition of limit is useful. So another way of saying a function is continuous is limit f of x as x goes to x sub 0 is equal to f of limit x goes to x sub 0 x. Okay, so f is continuous if limit can go inside f, or f and limit, or limit f equals f limit. Okay, so these are just a colloquial way of understanding limits, but in simple problems, it doesn't matter. In simple problems, they all look trivial, but sometimes if there are complicated expressions, so this may not be just x, f of some complicated function here, and you are taking the limit, you recognize that f is continuous, so you forget about f, you just calculate the limit of the complicated function inside, you get a number. If you get a number, you just evaluate f there. That's the limit. Okay, so that's why we mentioned this obvious equivalent version of continuity. Okay, so this is what you say among yourself. If f is continuous, limit go inside f, and this is what mathematicians say: limit operator and f are commutative. Okay, so we say it in that way so that nobody will understand it. Okay, so the next question is, how do we recognize continuous functions so that we can recognize, so I say I can know a function is continuous without calculating its limit, so that I can use to calculate limits there. Okay, so how to recognize continuous functions? Okay, so first we have the usual boring theorem, which says that if you have a complicated function and if you want to check if it is continuous or not, first you look at the small pieces. If the small pieces are continuous, then you can put them together. Okay, so that's what this limit is saying. Okay, so suppose f and g are continuous. So if you want this thing to be terribly boring, you must say that f and g are continuous at x sub 0. So f plus g, then f plus g is continuous. So I'm just using the general continuity. Then f plus g, f minus g, c times f, where c is constant. These are continuous functions. What else? Let's multiply them. F times g. We can also divide them if it doesn't give 0 over 0 division. So this is when g is different than 0 wherever you are calculating this. For example, if I'm looking at continuity at x sub 0, then here I want g of x sub 0 to be different than 0. Okay? So away from x sub 0, at certain points it may be 0. So this function may not be defined everywhere. But if at x sub 0 g is different than 0, then in some small neighborhood around x sub 0, this function will be defined. So when I say this, we are talking about f over g wherever it makes sense, wherever the denominator is different than 0. In that case, if f and g are continuous, their ratio is also continuous. Okay, so I think these are nice things. So finish this sentence, then these are continuous. Okay. Now using this theorem, just we did with the limit theorem, we can immediately say that a polynomial is continuous. Okay, so that was the reason why we immediately calculated the limit of a polynomial. Okay, so polynomials are of the, you can use this part to show that a polynomial is continuous. Then you can use this part to show that rational functions are continuous. Okay? You can take roots if you are not taking, if you are not entering into imaginary number world. If the root is a real number, then that's going to be a continuous function. Okay, so this follows because how do you prove these things? The only tool available to us are the theorems about limits, and we have such theorems about limits. You put them here, so whatever is true for limits will be true for continuous functions as far as combining them. Okay, so another thing is composition. F is continuous at x sub 0. Okay, let's say. And g is continuous at f of x sub 0. Okay, then g composite f is continuous at x sub 0. Okay, so it may sound boring, but a picture is illuminating. So we have this x-axis here, another x-axis here, let's say another x-axis here. This is x sub 0. Okay, so f takes this over here, f of x sub 0. F is continuous means that if you take a small neighborhood here, that small neighborhood will be here. So this is not the definition of continuity, but this is consequence of continuity. Okay, then g is, okay, so this is the point. G takes this point to some point here, which is g composite f at x sub 0. Or rather, let me do it first of all. It takes it to g of f of x sub 0. Okay. Now, if g is continuous, again, as a consequence of the definition, it will take a small neighborhood here to a small neighborhood here. So you see that I can always, if I restrict myself to a small neighborhood here, if I want everything to be in some small neighborhood here, I can start with a much smaller neighborhood here, and this composition will land in that neighborhood. Okay, so that means that if I forget this intermediate step, if I first write g composite f as a function, and I look at what it is doing at x sub 0, it will be behaving nicely from the figure. Okay, so g composite f will be also continuous. Okay, so this also now at this point I can only tell I can only extend our repertoire of continuous functions by saying that roots of continuous functions are continuous, provided that I'm always taking real roots. Okay, so with complex roots, you have to say a few more words, because with complex roots there will be several branches. You have to mention where you are standing, but we will not do that. Okay, so as a consequence, hence we now know, for example, root of f of x is continuous if f positive is continuous, or other roots whenever they make sense. Okay. Okay, so just because this is mathematics doesn't mean that we are doing meaningless things. So sometimes we write meaningless things, but they are wrong. Okay, so whenever things make sense, then we say something about it. So when you are taking a fifth root, 5/7th root, whatever, okay, if that makes sense, if you are taking the root of a continuous function, then this composite function is also going to be continuous. So again, what's the advantage of this? If I'm taking limits, I'll be able to go in. Okay, but so far, this is not exciting. Most interesting problems will appear with trigonometric functions, and trigonometric functions are continuous. We'll also do that. But let us first draw a few pictures to recognize continuity. So the simplest picture is something like this. You have a straight line. Okay, xy axis. You have a straight line, and at some point, for some reason, you don't have data for that, and this continues like this. Okay, so if you look at this thing, so this is x sub 0. Now this function is not defined at x sub 0. Okay, so it's not continuous there. Its limit exists. Okay, so let's say this number is, for example, I don't know, let's say 7. Who cares? Okay. So this function, let us call this y equals f of x. Well, we know what f of x is. F of x is a linear equation, but except that you say, I'm not defining at x sub 0. Okay. So you are the boss. You can do whatever you like. Okay. So f is not defined at x sub 0. So f is not continuous at x sub 0. So you see that I reached this conclusion without actually calculating the limit, okay? Because I don't need to calculate the limit. In the definition of continuity, I'll calculate the limit, I'll calculate the value of the function, and I'll check if they are the same. But the value of the function does not exist, so I stop there. Therefore, I don't need to calculate the limit, okay? So the function is not defined, stop there. The f is not continuous there, because one of the trivial conditions of continuity is that the function must accept a value there. Then you check if it accepts that value continuously. Here, however, limit exists. Limit as x goes to x sub 0 of f of x exists, and in the picture it is equal to 7. Okay, so let's look at, these are simple examples, but in real life complicated examples, only the graph will be complicated, and you'll again have a hole somewhere. If corresponding to hole, you don't have a value, the function is not defined. So let's look at the next simple case. Again, we have, let's try to do the same thing. Again, we have this. This is x sub 0. This is 7. This is y equals f of x. And for some reason, I decided that the function will take this value here, let's say 27. Okay? The picture drawn not to scale. Okay? So here, f of x sub 0 equals 27. It exists. I calculate the limit as x goes to x sub 0 f of x. From the figure, it is 7, right? From the 7. They are not the same. So f is not continuous at x sub 0. Okay, so now we know what we have to do. There must be a value, so I put a value, but I put it in a wrong place. So in order to make this continuous, I have to bring it here. Okay, so in the last example, so this is my y equals f of x. This is x sub 0, and corresponding to this, I have 7. Okay, now I calculate f of x sub 0. Well, I know that the value is this. I calculate the limit f of x as x goes to x sub 0. Again, since this is the only information given, I calculate the limit by looking at the graph. The limit is here because the graph approaches to this value, as I did in both of these. This is 7. They both exist and are the same. They are the same. So f is continuous at x sub 0. Okay? So as I said, in more complicated exam-like questions, the only thing that will change is the shape of the graph. But this is the idea behind checking continuity at a certain point. No matter how complicated the graph is, you'll only concentrate at what happens to the graph here. Okay? So in more obvious cases, for example, the limit may not exist. So let us look at those cases also. So we have a function like this. Okay, so let's make this way. Let's make this way. Okay, so this is x sub 0. So this number is 7. This number is 8. This number is 9. Okay, so this is y equals f of x. So now here in this picture, first we apply the usual definition of continuity that we don't tell anyone because it's not scientific. Can I draw the graph of this without taking my hand off the board? I cannot. Okay, so I come here, then I go there, then I do this. So I took my hand off the board, so it's not continuous. Okay, now that's our guess. This function is not continuous. Okay, again, let me repeat that this is a simple example, but the procedure is the same no matter how complicated the example is. Okay? First, I calculate f of x sub 0 to check if it exists. F of x sub 0, from the data, it is equal to 8. Okay, so it exists. Now I calculate the limit, but for the limit, you see, you have to look at right and left limits. Here, limit as x approaches to x sub 0 from below. So I'm approaching from below. I go to 7. Limit x approaching to x sub 0 from above. From above, I come to 9. F of x, limit is 9. Okay. They are different. So the limit does not exist. Limit x goes to x sub 0, f of x does not exist. Okay, so it turns out that I calculated this for no reason. It's not useful because as soon as I know this, the limit does not exist at that point. So f is not continuous at x sub 0. Okay. So I think this is as complicated as it can get. As I said, the graph may be very complicated, but continuity at a point, this is what you are going to look. Is the information available to you allows you to calculate the function at that point, the right and left limits. Now, if this information, if all these numbers are the same, the function is continuous at that point. If not, it's not continuous at that point. Okay, so that's all. So let me see if we have. We have some boringly obvious terminology. You see, the hidden concept behind this is apparent in this example. When we check the limit, we always look at the right limit and left limit. If one of these limits does not make sense, for example, it was possible that the function is not defined on this side, okay? But then if the limit is equal to the value, if the right limit is equal to the value of the function, we all agree that it's a nice function, okay? So there is no reason to say that the function is not continuous. So we will make that agreement. Let me draw a picture at end points. So this is generally the terminology for this thing. So f is defined. Okay, so I'm drawing these things with blue now. Let me continue with that. So suppose f is defined on an interval only. Okay, so this is a, this is b. The function is defined here. The function takes this value, does something, comes over here, and at that endpoint, my data is such that this is the value of the function. So this thing is 7, this thing is 8, and this thing is 10. Okay? So by looking at this function, according to our expectation, the function is continuous inside because the graph is smooth, the right left limits exist, the function takes the value of its limit. At this point, okay, we all agree that the function is nice because it approaches to its limit and takes the limit. So the function is nice here. But at this point, the function is not nice. Well, it's a nice function, but we made a different, we have a different taste for niceness. We want the function to take the value it takes as in the limit. Okay, so in the limit, the function takes this value, but actually the value of the function is this. Okay, so we don't like these things. So at this endpoint, the function is bad. Okay, now instead of nice and bad, if you say nice and bad, everybody understands you. Now you are educated, so you have to sound a little bit mysterious. So we say the function is continuous on the left-hand side, and this is discontinuous on the right-hand side. Okay, so at a, at x equals a, okay, f of a equals 8. Limit as x goes to a. But now limit as x goes to a does not make sense because when you talk about limit, it is inherent that you mean right and left limits. Here, left limit does not exist because there are no values of f there. So here you are only interested at the right limit. Okay, so this is f of x that exists, and that's also equal to 8. Okay, so f is continuous at a. Okay. On the other hand, at x equals b, f of b is defined. That is, how did we define it? 10. And now we look at limit of f of x as x goes to b. But again, this time, limit on this side does not make sense because there's no f there. Well, we are only looking at limit here. So this approaches to b from below, and that also turns out, this turns out to be 8 in this case. Okay, so they are not the same. So f is not continuous at b. Okay, so this one of them is called continuity on the right, one of them is called continuity on the left. I can never memorize which one is which. Okay, so this is the concept. Okay, so if we are at the end point, we drop one of the conditions in an obvious way. When we are talking about limit, one side of the limit does not exist. So I do not make it a case against f because f does not exist there. Whatever is available to f, f is obeying all the conditions within its capacity. So I say f is continuous. But on this side, f is committing a big big crime. It has one-sided limit, which it can only have, but then it's not accepting that value. It's accepting something else. Okay, so then I say you are not, I'll call you discontinuous at that point. Okay, if a function is not continuous, you can call it discontinuous. Okay, so this is what happens, or, well, this is how we talk about the endpoints. So let me see what we have after this. Polynomials, rational functions, we did that. Okay, so there is a boring, complicated example. I'll skip this. Okay, let's look at trigonometric functions, because the only non-trivial, interesting things will be composing trigonometric functions with the polynomials or rational functions. Okay, so they are next to impossible to do with epsilon and deltas. So if we know that sine and cosine are, or if we only know that sine is continuous at 0, then from there we can get almost everything, and then we combine it, these things. For example, at that point, we don't know, we don't have a technique to show that, say, sine cube of x squared over 2 is continuous. But if you draw the graph of this, that obeys the condition that you can draw the graph without taking your hand off the board, or the graph is not broken. There are no holes in the graph. Okay? So it must be continuous. But how do we show this? So we have to start from the basics. We have to check that, first of all, sine is continuous at x equals 0. Okay? And then by using addition theorems, we'll show that sine is continuous everywhere. Okay, then from there, the rest should be easy, because cosine is square root of 1 minus sine square. Okay, if sine is continuous, sine square is continuous, because product of continuous functions is continuous. 1 minus a continuous function is continuous. It's always positive or 0, so I can safely talk about the square root. So the square root is continuous, but the square root is cosinus. So I don't need to do anything about cosinus. So all it remains is to check that sine is continuous at 0, and using that I can show that it is continuous at everywhere else. Then I'll need this boring example. Okay, certain basic things look boring, but then they are very useful. So let me start with, okay, now trigonometric functions. Okay, so first sine function. Let's see, so this is the unit circle, 1. And I have this point here. So this point is what? Cosine x, sine x. Okay, so, well, we can also do the following. We can see what happens as this is, let me call this theta so that it looks very geometric. Okay, and this is theta. So what happens to, let's start with sine x. So what is limit as theta goes to 0 from the right, let's say, so that this picture will make sense, sine theta. Okay, so sine theta is this height, right? And from this picture, we know that that will go to 0. But we can also use the fact that this length is less than this length. Okay, so this is equal to, use the fact that sine theta is less than theta for small theta. Okay, and since we are here, so from here for small theta, sine, you see sine is positive, and that's less than theta. 0 goes to 0, theta goes to 0, as theta goes to 0. That's trivial. Okay, so by sandwich theorem, sine theta goes to 0. Okay, so sine theta, limit of sine theta is 0. Limit of sine theta as theta goes to 0 is 0. Okay. Now, if theta is negative, okay, if theta is negative, then you see I'll put minus theta here and choose a positive theta. Sine minus theta is minus sine theta with theta positive. Minus sine comes out of the limit operation. So I'm again calculating sine theta with positive theta as theta goes to 0. It is 0, and I keep this minus 1 here. Minus 1 times 0 will not change the result. So around here, this calculation works. Sine theta, limit of sine theta as theta goes to 0 is 0. Okay. So what about limit limit as theta goes to some other number a of sine theta? Okay, so let me see. There was some calculation here. Here, for this, we need the following technical observation. It is again trivial, but we have to observe this. Remember, we are following the tradition of Euclid of 2,000 years ago. Okay, so you have everything you say here must depend on what you said before. So here we don't want to use something that we didn't say before, even though it is very trivial. Okay, so it is this thing. We use the following observation, or you can prove this. So what is this? Limit as h goes to 0 of f of a plus h is equal to f of a if and only if f is continuous at a. Okay, so I will not prove this because it is easy. You just change variables here, or you can draw pictures. You can use epsilon delta. Okay, so it's an easy proof since we are not doing proofs. But you see, now here comes the following observation useful. Remember that one of the equivalent definitions of continuity is that you can, if f is a continuous function, you can change the places of these. Okay, so when h goes inside, you will have, when this limit goes inside, you will have limit of a plus h as h goes to 0. Okay, so that will immediately make this a. You can do this. You can change the places of these when f is continuous at this point. Okay, so that was one of the easy observations. Okay, now we'll use this for sine functions. Okay, now we apply this. So we apply this as follows. Okay. So I look at limit as, say, h goes to 0 of sine. I'm trying to understand this, so theta plus h. Okay. This is, but I know that, so what did I do here? Okay, so this is what I have to calculate. So this is, I have to calculate limit h goes to 0, sine theta times cosine h plus sine h times cosine theta. Okay, so here, okay, so I know that cosine x is equal to positive square root of 1 minus sine square x. Okay, so so this is continuous. Sine is continuous at x equals 0. Okay, so sine squared product of two continuous function is continuous. A constant function is obviously continuous. Okay, there is no holes in it. Sum of two continuous functions is continuous. This sum is always positive, so taking square root is a meaningful number always. So that's continuous. Okay, so this tells me that cosine x is continuous at x equals 0. Okay, now using these, I have the following. Also, I have limit of a sum is sum of limits. Limit of a product is product of limits, but this is constant. Okay, we are only taking limit as h goes to 0. So only h is moving, theta is fixed. So this is a constant, so this limit comes here. So what I have is the following. Sine theta, which is a constant, limit h goes to 0 of cosine h, plus limit as h goes to 0 of sine h, and then I have this constant cosine theta. Okay? Now that I break it into this, I can easily calculate, because I know that this limit is 1, because you take the limit here as x goes to 0, you'll get 1. Okay? So this is sine theta times 1 plus 0 times some constant. So we have just sine theta. Okay, so what did we do? We did this part. Our calculations gave us this part. Okay, but this observation tells that if you obtain this, then f is continuous at that point. Okay, so using the observation, using the above observation, sine is continuous at theta. Okay. Now again using this, okay, this now tells us that cosine is continuous at theta, at any theta. You check that we started with theta, arbitrary theta. Okay, so here, what did I do? I used fixed theta. So let me do this. Okay, so this is a general question. Here we assume theta as fixed. Pick an arbitrary fixed theta. Okay, so we are checking continuity at theta. Okay, so this is what we did. Okay, it looks complicated because every time you write algebraic expressions, it looks complicated, but the idea is very simple. Draw the graph of sine. There are no holes in the graph of sine, so sine is continuous. Now, does this observation follow from technical definitions we wrote? So this part is only asserting our observation that there are no holes in the graph of sine theta. Okay, so technically we do it once so that we can sleep comfortably and confidently at night. So we are not going to repeat these arguments. So what we are going to use is that sine and cosine are continuous functions at every point. Okay, so that's what you should know. Okay, so next, if I have these things, then I can combine sine and cosine with each other to obtain every trigonometric function. All trigonometric functions you see, except inverse trigonometric functions, they are all obtained as ratios of these things. So sine over cosine or cosine over sine, 1 over sine, 1 over cosine, etc. So they are all going to be continuous wherever they are defined. If there is no division by 0, then it's going to be a continuous function, because that was our boring theorem about limits and continuous functions. You can divide them. If it makes sense, then it is nice. That was the technical thing. Okay, so we can make a note of this, saying that all trigonometric functions are continuous. Okay, so you can forget all the calculations we did. That's just to convince ourselves that our instincts are correct. Sine and cosine are continuous everywhere. Okay. Then tangent theta, which is sine theta over cosine theta, etc., are all continuous wherever, continuous on their domains. Okay, so on their domain means that they are defined there, no zero division. Okay, because the other functions, tangent, cotangent, secant, cosecant, they are obtained as rational functions of sines and cosines, so they will be continuous as long as you don't attempt to divide by zero. Okay, so now we are at a point to see that complicated functions are continuous without doing any epsilon delta argument. Okay, so this is where our definition of continuity and our discussion about continuous functions are all come to a conclusion. Okay, so finally, functions such as, okay, so x cubed sine x squared plus 1 over x to the 4 plus x squared plus 7. Or let's see, let's write another one. Sine x cubed plus 71 divided by cosine square x plus 1 over x squared plus 8 plus 2 are continuous. Okay, so when we say are continuous, that means they are continuous everywhere if there is no zero division. Okay, so you see that how would I, if I used only the definition of continuity, how would I know that this is continuous? I have first of all calculate its limit, but calculating its limit is horrible. Okay, but I immediately now know that I can just calculate this. Sine is cosine, sine is continuous, cosine is continuous, squares, polynomials, rational functions, addition, division, they are all continuous things. So all I have to do is plug in the value wherever I'm trying to find the limit. I just plug in the value and that will give me the limit. Okay, so the whole idea of recognizing continuous functions was to calculate limits easily. Okay, so their limits are easy to calculate. Just plug in the value. Okay, so this is where theory goes upside down. Okay, now we recognize continuous functions without calculating any limits. And we use now these functions, we use the information of continuity to calculate limits. The idea was to calculate limits. Why? Because next week we'll start with derivatives, and derivatives rely on calculating strange ratios. And it is always the case that you have 0 over 0. And if you know L'Hopital's rule, you can't use L'Hopital's rule there because L'Hopital's rule will be developed after you understand these ratios which will define your derivatives. Okay, so much for the concept of continuity. On Friday, I'll solve problems, maybe talk a little bit more about continuous functions, and to our surprise, we'll have a quiz. Okay?